Aviation fuels, especially for military jets, are the most costly fuels in the energy market today. We could have significant positive impacts on national energy security, the rural economy, and the environment if we can find a sustainable alternative to petroleum-based jet fuels in the U.S. First-generation biofuels, fuel ethanol, are made from sugars and starch. These feedstocks may conflict with human and animal food sources. Therefore, we must produce second and third generation biofuels from non-food biomass feedstocks. Examples are wood and straw residues from agriculture and forestry, non-food oil crops capable of being grown on marginal or non-arable land, organic fractions from urban waste, and algae-based feedstocks. Today I'm going to show you an example of the raw feedstocks that we use and the products produced. This is camelina, one of the oil seeds that we process through the cold press method. And when we do that, the oil that is expelled is right here. So this is camelina oil. That camelina oil is further processed through a hydrocracking reactor and produces a drop-in fuel. This drop-in fuel is very close in characteristics to liquid petroleum transportation fuels. And to give you an example today, I'm going to burn a little bit of it. These technologies and feedstocks promise to be more sustainable, offering significant reductions to greenhouse gas emissions and are less sensitive to fluctuations in the feedstock costs. This project is funded by the Department of Transportation through the North Central Regional Sun Grant Center. The method used to extract vegetable oil from oilseeds is a critical step towards successful biojet fuel production. Cold press technology has many advantages. It is a continuous process that requires minimal labor, produces good quality oil, has low capital costs, and is suitable for small-scale production in the rural areas where the feedstock is grown. The oil extraction efficiency of the cold press method can be as high as 89%. To start the process, the temperature and rotating speed of the screw are stabilized at the optimal conditions for oil expulsion. The oil seeds are fed into the hopper and then enter the screw, where the oil seeds are broken and compressed by the screw, forcing the oils out of the seeds through the steel mesh. The residual meal is extruded out through the nozzle at the front of the screw. The expelled oils are then upgraded to drop-in fuels for production of biojet fuel using a catalytic cracking reactor. The hydrocracking reactor takes the larger or longer molecular weight fatty acid components in the vegetable oil and breaks them into smaller or shorter molecules by using appropriate catalysts at optimal reaction conditions. These smaller molecules are the drop-in fuel products. The yield and quality of drop-in fuels produced for biojet fuels depends on vegetable oil feedstock, catalyst, and reaction conditions. To date, we have been able to achieve drop-in fuel yields as high as 70%. The next step for this research will be to correlate the extraction method and oil type to drop-in fuel yield. This will allow us to determine the most optimal methods and processing conditions to achieve maximum yield for each type of oilseed.